In that last section, we came across that the derivative of natural log is 1 over x. It's a nice statement, and we're going to use this along with properties of logarithms to differentiate somewhat complex statements. If we have our function f of x is equal to x to the x, well, in the past, we've got a combination of power rule because we've got x to the n. Well, the derivative of x to the n gets us n x to the n minus 1. But it's not quite a power rule. It is also an exponential function, where if we've got the exponential base b, the derivative of exponential base b comes up to be the natural log of b multiplied by that statement. Well, it's a kind of a combination of the two of them. Which rule do we follow? Which rule do we use? I'm not so sure. But we're going to take advantage of the derivative of natural log and use something that we call logarithmic differentiation. This applies the derivative of natural log along with properties of logarithms. Sometimes we have complicated functions involving products, quotients, or powers that are rather messy altogether. Here, we're going to take a look at how we can break those apart using what we're going to call logarithmic differentiation. So here's our example start. Y equals x to the 3/4 multiplied by the square root of x squared plus 1 all over 3x plus 2 to the 5th power. Yikes. So there's product rule, there's quotient rule, and chain rule, and there's the quotient rule all mixed in there. That's a mess. That we could do it, but that might not be so much fun. Here's our strategy. We're going to call it logarithmic differentiation. I'm going to take the log, natural log, of both sides. So I'm going to take natural log of y, and that's going to be equal to the natural log of x to the 3/4 multiplied by x squared plus 1 to the 1/2, because the square root is the 1/2 exponent, divided by 3x plus 2 raised to the 5th power. Now you might be thinking at first that we've got a log mixed in there. Why would I ever want to do that? Well, we're going to recall properties of logarithms. So if I have the log of a product, I can rewrite that as the sum of the log of the individual factors. We have that if we have a quotient, log of a quotient is equivalent to saying it's log of the numerator to subtract log of the denominator. And we also have the natural log of exponent on this topic. That turns into multiplication by that exponent. We're going to apply those three properties to this statement. So what I see is we have an exponent, we have multiplication, there's another exponent, there's division, there's an exponent, and okay. Well, that product, we can separate that. That division, we can separate that. Those exponents, we can take those out as a product. So applying properties of logarithms, we can turn this statement into the natural log of y equals 3/4 natural log of x, added to that 1/2 natural log of x squared plus 1, subtract 5 multiplied by the natural log of 3x plus 2. So that exponent, 3/4, came out front of the x as multiplication. That product between the x to the 3/4 and the square root of x squared plus 1 will split up as addition. The 1/2 exponent came out as a product. We're subtracting because we were dividing by the statement 3x plus 2, and that 5th power came out as a product. Now note that x squared plus 1 or the 3x plus 2 cannot be split because that is a sum inside a logarithm, not a product, not a quotient. Now, let's differentiate. We know the derivative of each of these is considerably easier. So I'm going to apply my derivative to the entire statement. Derivative of natural log of y is 1 over y multiplied by dy dx. Think implicit differentiation. 3/4 times the derivative of natural log of x. Well, that is 3/4 multiplied by 1 over x. That's it. Add to that, well, we've got 1/2 multiplied by the derivative of natural log x squared plus 1. So that is 1 over 2 x squared plus 1. Chain rule, derivative of x squared plus 1 is 2x. Make note of that. Subtract 5 multiplied by the derivative of natural log of 3x plus 2. So that gets us 3x plus 2. Chain rule is going to be multiplied by 3. We've got 5 times 3. Now, rewriting, we want to solve for dy dx. On the left side, we have 1 over y, so we're going to multiply by y. That gets us dy dx is y multiplied by 3 over 4x plus x over x squared plus 1, subtract 15 over 3x plus 2. Our last final step, we don't want this in terms of y and x, so we're going to replace that y. Y is our initial statement. Replacing, our derivative becomes x to the 3/4 multiplied by square root of x squared plus 1 divided by 3x plus 2 quantity raised to the 5th power, that's y, multiplied by what we just found. Not necessarily simplified in some ways, but we found the derivative, and we can take the derivative without needing product, quotient, and chain rules. Let's do another one. So here's our process. We're going to take natural log of both sides of our equation, y equals f of x. Use those laws of properties of logarithms to simplify, to expand. We're going to differentiate implicitly with respect to x and solve a resulting equation for y prime or dy dx. Let's try another one. Here we have x raised to the square root of x. Oh boy, not sure if we should use the exponential base rule or the power rule. So we're going to take the natural log of both sides. We have natural log of the left, y, equals natural log of x raised to the square root of x. This then gives us the natural log of y, and because we have an exponent inside our log, this is the square root of x multiplied by the natural log of x. It is just the product rule. Differentiating, we have 1 over y dy dx, derivative of the first, 1 over 2 root x, keep the second the same, ln x. Add to that the first times the derivative of the second. Derivative of natural log is 1 over x, so we have square root of x over x. So we have 1 over y multiplied by dy dx is equal to natural log x over 2 root x plus 1 over square root of x. Solving for dy dx, I'm going to multiply dy dx is equal to y multiplied by natural log of x over 2 root x plus 1 over root x. And I'm going to replace with the definition for y. So we have x, the square root of x, multiplied by natural log x over 2 root x plus 1 over root x. Not the prettiest, but we have a way of differentiating any function that might otherwise look like a mess. There you go. Try it out. See you later.